In the previous episode, I showed you the platform which we are going to build this entire series. If you are new here, my name is Arbaz and welcome to my channel Learn with DevOps Engineer. I spent over 12 years building and operating production infrastructure across DevOps, cloud, and platform engineering. Now, when most people hear Kubernetes, they think that's where they should start. But that's not how real companies work. No company starts by building Kubernetes platform. Most of the companies will start with one single application, the two on one server with a few users. As the company grows, new challenges appear, and that's what drives infrastructure to evolve. So, before we install Docker or create Kubernetes cluster, we need to answer one important question. How did modern infrastructure evolve to where it is today? Why did we move from physical servers to virtual machines to the cloud and then eventually to containers? Because Kubernetes didn't appear overnight. It is the result of decades of solving real production problems. And in this episode, we are going to follow the entire journey from physical servers to Kubernetes step by step. Let's imagine we have just started a company. We are building a simple application. It could be e-commerce application or it could be a project management tool. It could be a banking application or an internal platform used by employees. It can be any business. The exact business is not important here. The exact business is not important here. What matters is that applications need to run somewhere. At the beginning, our requirement is very simple. So we need something like a computer power, right? Then we would need some memory. We need some storage, and also we need something like networking and operating system. Today, we can create a cloud VM within minutes. But infrastructure was not always this much easy. To understand where we are going, we need to go back to where the industry started. Before cloud computing, companies purchased physical hardware. A physical hardware is a real machine which will have something like the CPU, which you are seeing here, memory, storage, operating system, networking. The company would purchase the hardware, install it inside a data center, connect it to the network, then install the operating system, and finally, we are going to deploy the application. It worked perfectly fine. In fact, many important systems still on prem. So, in the corporate terms, we call this as on prem, wherein physical servers in a data center you are trying to operate it directly. But this physical server era It created several major challenges. Okay, now we are going to discuss few major problems. I cannot cover every problem, but I'll do my best to cover the problems which I personally have seen during this particular physical server era. Now let's discuss about problem number 1. Hardware was expensive. Imagine your application needs 2 CPU, 4 gigabytes of memory, and then 50 gigabytes of storage. But the server might contain 32 CPU followed by 32 GB of memory and 1 terabyte of storage. Most of the capacity would go unused. In this scenario, the company paid for the entire server, even if the application is using a small percentage of it. This is called poor resource utilization. So, for example, physical server capacity is 100%, application is used 15%, unused capacity is 85%. The server was very powerful, but most of the power was, let's say, sitting idle. This was problem number 1. Today, we can provision a cloud machine within minutes. Previously, infrastructure team, for example, I personally followed this whole process. First, I used to estimate the capacity, followed by request a budget. Then I had to select the hardware, which one to buy exactly. Then place an order. Wait for delivery. Usually it used to take a lot of time, sometimes 3 months, sometimes even 6 months. So I need to wait for the hardware to get delivered. Once the hardware is delivered, I need to install the server. That means configure the networking, talk to the networking team, and also configure this networking part. I mean, plugging the cables and stuff, followed by installing the operating system. Then application security controls, followed by finally we are going to deploy the application. These are some of the steps that I remember doing it. There might be few more, that's okay, but overall I would like to give a picture how the infrastructure provisioning looked in the past. Now this could take, let's say, for example, weeks or months, majorly months. I mean, in my experience, it took months, especially, not weeks. I mean, for some people it can be a bit fast. But now imagine telling this to the development team, saying your server will be available within a month or maybe within 6 months. How does that look like? This made experimentation very slow. These days, I mean, it's very fast because everything can be, spin up within minutes, and developers can, spin up very fast and also can destroy the servers very fast. It almost made scaling very difficult. We had to plan a lot of stuff in advance because scaling would become a bottleneck here. Not only from my own experience, it was across the world, across the companies, across the projects. There had to be more and more planning in advance for, the scaling part, or maybe what kind of hardware, how much is, let's say, required. We have to calculate so many different things in advance, then only we were able to order stuff. Now let's discuss about problem number 3. Applications were tightly coupled to the hardware. Suppose an application was installed. So we were installing on the physical server. Over time, that machine accumulated operating system configuration, followed by runtime dependencies, then followed by application files, security settings, manual changes. The server slowly became unique. People sometimes used to call this as pets. They had, different names. They were carefully maintained because dependencies were, a common issue there. If I had to change one version, then I had to be very, very careful because I'm going to destroy the full server. And if one failed, restoring was very, very difficult because nobody knew every change that had been made over the years. Even today, this is a very, very big problem. Not only in the past, even today, this is a big problem. Imagine our application became popular. Traffic will increase, right? The server reaches its limits. Even today, it happens. What do we do? You might have a question running in your mind. What do we do? We need another physical machine. That means another purchase, right? Another installation, another configuration. Like the whole process which we did previously, we are going to follow that. The business could grow faster than the infra team could provide the capacity. That led to our next part, virtualization. Virtualization allowed one physical server to behave like multiple independent computers. The hypervisor divided server into multiple virtual machines. That means each virtual machine will have its own CPU, own memory, own storage, and own operating system. From the application point of view, it looked like a it looked like a real server. This improved resource utilization. Why virtual machines were powerful? Let's say one physical server had 64 gigabytes of memory. Instead of running one application that used 8 gigabytes, now we could create something like this. VM1 will use 8 gigabytes, VM2 will use 16, VM3 will 8 gigabytes once again, VM4 and VM5, and so on. This gave companies better hardware utilization, the problem which I was discussing in the beginning. Then isolation between applications. Previously, we did not had any isolation. Everything was, let's say, installed on the same physical server, followed by faster provisioning. Then easier backups as well. Also easy to migrate. More flexible resource allocation. Virtual machines made massive improvement, but they did not eliminate all problems. Virtual machines improved infrastructure problems, but they introduced their own overhead. Every virtual machine required its own operating system, as many of you know that. That means each VM contained kernel components, system libraries, background services, security updates, monitoring agents, runtime packages. Even if the application is small, the virtual machine could be very large. Now imagine running hundreds or thousands of virtual machines. The infrastructure team had to manage operating system, security vulnerabilities, very important point here, then runtime versions, configuration drift, VM images, backups, networking, so on. There are so many different things that the infrastructure team need to manage. Provisioning became faster than physical servers, but it was not still instant. A VM might take several minutes to boot, and applications still could behave differently across environments. This is one of the most famous problems in software engineering. If you are working for a very long time, definitely you can relate to what I am discussing in this section. It works on my machine. A developer writes an application on a laptop. It works perfectly. Then the application moves to a test server. It fails. Why? Because of n number of reasons. For example, because environments are different. The developer can have Python 3.12 version, but the server where it is being tested, it can have 3.9 version. The developer might have one library version. The production server might have another library version. This is where the conversation becomes it works on my machine. And the operation teams respond, but your machine is not production. This problem became very painful as application grew more complex. A modern application could require a runtime, a framework, dependencies, system libraries, environment variables, configuration files, network settings, supporting services. Teams needed a consistent way to package their applications and also run it properly. But before containers took over, another major shift happened. That was cloud computing. Cloud computing did not eliminate physical servers. Also, cloud providers like AWS, Azure, Google Cloud still operate physical data centers. Major difference is ownership and access. Instead of purchasing, like I was doing, purchasing hardware myself, I can rent infrastructure from a cloud provider. It can be any cloud provider: Azure, AWS, Google Cloud, Oracle Cloud, VMware Cloud, or some other cloud. So I can rent, for example, I can request for a virtual machine, I can request for a VM, I can request for a database, I can request for a VNet, I can request storage. I can request a Kubernetes cluster. There is a lot of stuff which we can rent it. The infrastructure model changed from buy hardware, wait for it, install, configure, and use to request resource, provision automatically, use, and pay for consumption. That was revolutionary. Cloud platforms solved several business problems. Like, for example, faster provisioning. I Instead of waiting for weeks or months, I can spin up a server within minutes. This was one of the major problem cloud platforms were solving. Then we have pay as you go pricing. Companies did not always need large upfront hardware requirements or investments, as I said. According to the individual project or team's requirement, you can pay for the necessary hardware. This is, let's say, another one of the major problem the cloud providers solved, followed by global regions. That means we don't need to buy physical hardware across multiple different locations. In my case, we had multiple places. For example, we had in the United States, Canada, Singapore, USA, we had multiple different physical servers. With the cloud providers, you can spin up servers or, let's say, virtual machines, databases anywhere globally within minutes. Then elastic capacity. That means we can increase or decrease resources according to our own requirements. If we don't need something, we can delete it. And another favorite part is automation. My favorite one, once again, infrastructure, wherein I can use tools like, for example, Terraform to automate the full infrastructure across multiple clouds. It can be, let's say, Azure Cloud, AWS Cloud, Google Cloud, any cloud. Before this, I was using more of shell scripting and some other, configuration tools to manage my physical servers. But this is much more easier, and we have multiple API providers for this as well. Managed services. Companies could use managed database, for example, managed queues, storage as well, managed storage, and then also managed Kubernetes clusters and many other services. Cloud computing made infrastructure more accessible, but something important did not change. We were still deploying applications onto the virtual machines. Now, let's return to our own platform. At this stage, our architecture could look simple like this. For example, we are starting with a small application. This is completely reasonable here. We do not need Kubernetes. We do not need service mesh as well. And also we don't need 50 microservices. We need a machine that can run our application. In the next episode, we can create a Linux virtual machine and we can begin running our first application. But before we do that, we need to solve the application packaging problem. Now, imagine our application contains a front end, a back end, a database. It can be any database, a background worker. Each part will have different requirements. Front end may require Node.js, back end may require Python or Java. Database can be Postgres or MySQL. It depends. Worker might need additional libraries. Without containers, we may install everything on this physical Linux server. as you can see in this image. At first, it works perfectly fine. Then a second application arrives. It needs another Node.js version. Then we get a third application. It would require different Python or Java version. One upgrade breaks another service. The server becomes increasingly difficult to maintain. This is sometimes called dependency hell. Containers introduced a different approach. Instead of installing all the dependencies directly on the server, we package the application together with what exactly it needs. For example, a container image can include application code, runtime, libraries, dependencies, default configuration. Then this particular container image can directly run on a laptop, a test server, a CI/CD runner, a Kubernetes node. The environment becomes consistent across multiple different servers. Build once, run consistently. Containers Containers are also lightweight when compared to virtual machines because they share the host operating system. This distinction is very important between virtual machines and containers. A physical server will have a hypervisor with a virtual hardware and guest operating system followed by an application. The same goes with the containers. Physical or virtual server followed by host operating system will have a container runtime. Then followed by we are going to have multiple different containers. Because containers do not require a complete operating system for every application instance. They are generally smaller. Whereas virtual machine will need its own operating system. Containers are way smaller. They are also very faster to start, easier to distribute. For example, we can distribute images very easily, whereas virtual machines also we can do, but it's a bit difficult. Then more efficient for application packaging. One more important point I would like to add here: containers and virtual machines are not enemies. Even today, many companies, many projects are running on a virtual machine. In many companies, in many different projects, we have physical server followed by a hypervisor. We have a virtual machine. Then we have a container runtime. And finally, we are running containers as well. This is very common in the cloud environments as well. And also, for example, Kubernetes worker node itself is a virtual machine. Inside that, we'll have a container runtime and we are running containers. This is very common. Containers solved packaging and consistency problem, but they did not solve high availability. They did not solve multi-server scheduling. They also did not solve automatic recovery, load balancing, scaling, secret management. I mean, there are so many different problems that containers itself did not solve. Docker can run containers. Excellent. But once we have many containers running across many machines, a new problem appears. Who decides where each container is going to run? Who performs a deployment? Who will maintain number of replicas? This is the problem container orchestration was created to solve. And eventually, Kubernetes became dominant system for that job. But we should not jump there yet. First, we need to experience why containers were so powerful. Now let's try to summarize the full journey. Every layer solved a problem created or exposed by the previous layer. Physical servers were not bad. They were simply difficult to provision and often underutilized. Virtual machines were not bad either. They gave us isolation and better resource usage. Cloud computing did not replace virtualization. It made infrastructure available on demand. Containers did not replace virtual machines. They made application packaging faster and more consistent. And finally, Kubernetes did not replace Docker. It solved the operational challenges running many containers across many machines. This is the bigger picture. In the beginning of the episode, we looked at a platform containing so many different tools. For example, Kubernetes, Cilium, Prometheus, Grafana, and so on. We saw so many different icons with a platform architecture diagram, with a neat diagram. That platform looks very, very complicated because it represents the final result of many production problems. But today, our platform is very, very small. We have a Linux virtual machine. On that, we have an application, and there are some users. This is, let's say, a platform v0.0. This is where we are going to begin. We are not going to add Kubernetes because it is popular. We are not going to install Prometheus because every architecture diagram includes it. We are not going to let the platform grow naturally. Every tool must earn its place. There is something important I want to make it clear. Modern does not always mean better, and complicated does not always mean production grade. A small company running a stable application on two virtual machines can be more production ready than a badly managed Kubernetes cluster with 20 tools. The right architecture depends on scale, team size, operational experience, reliability requirements, security requirements, cost, business needs. Kubernetes is not the starting point for every company, and it should not be. Our job as engineers is not to use maximum number of tools. Our job is to solve business problems with the simplest system that meets requirements. Throughout this series, we are going to ask ourselves, does our platform actually need this technology? That question is more important than knowing the installation command. In the next episode, we will move from history to implementation. We are going to create a Linux server, connect it securely, install Docker, build our first container image, run the application inside a container, inspect the container, stop it, restart it, break it, then finally troubleshoot it. And most importantly, we will understand why Docker changed the way applications are built and delivered. Thank you for watching. I'll see you in the next episode.